Yeah, hi. So I would like to first thank the organizer for this opportunity to speak here. So theme of this talk is little different. So this is how you can probe VSM physics with gravitational waves, like primordial gravitational waves. So the title of the talk is Dark Neutrino Interactions Make Gravitational Wave Blue. This is the work I have done in collaboration with Rishi Khatri and Tuhin Rai from TIFR. And so let's start. So first, let me give you a timeline of this problem and what this problem is all about. So we have at very high energies some sources that produce primordial gravitational waves, let's say inflation or some other sources. And you detect these gravitational waves through CMB or direct detection at present times or through CMB. So the idea is that when you detect some gravitational wave, you can tell something about his features, his UV features, like something like, let's say, NT. So we already have some information about the amplitude R, and let's say we detect gravitational wave with sufficient enough accuracy, then we will be able to measure the spectral tilt, which is NT, and then we can actually rule out a large class of inflationary models through these informations. So the idea is that you detect something at the present times and you straight away know what the UV physics is. But what actually I will show in this talk is this simplified picture is not quite accurate, because there are some medium effects that can affect your gravitational wave propagation and which can be very important. Like, let's say, so the propagation of these gravitational waves actually depend crucially on the anisotropic stress of the medium. And you all know that free-streaming particles affect this anisotropic stress. So in principle, any new interaction of your free-streaming particles can in principle change, and in principle have an imprint on whatever you are detecting. So we have only one free-streaming particle, which is neutrino. So, and we actually will see that these neutrino interactions, when you introduce this new neutrino interaction, some of these features of these new neutrino interactions can be very similar to some of the UV properties of the gravitational waves. So in that sense, there is a degeneracy, and entangling this effect can be very challenging. Okay, so this we will see at the end of this, through this talk. And so this is kind of a proof of principle kind of thing, that we show that this effect exists and kind of say what the magnitude of this effect is. So let's start. So the interaction of the neutrinos I'm talking about is beyond the standard model interaction of the neutrinos. We already know what standard model neutrino interactions are up to some point. So we need a model where we can incorporate these new neutrino interactions. So we can do it in various different ways. It's a model-dependent questions. So for this purpose of this work, we choose to couple neutrinos with dark matter. So this is actually motivated from the fact that dark matter neutrino interaction can in principle solve some small scale problem on the CDM. But qualitatively, all the results that we will see in this talk actually also holds for any general kind of BSM neutrino interactions, like neutrino self interaction or anything other than that. Anything that is a new interaction. So this is just a model of neutrino interaction. So you write it in a standard model gauge invariant way, and after selective symmetry breaking, you get a Yukawa-like operator. So here, this is dark matter, and my psi is dark matter, and chi is mediator. And if you take this interaction, what will happen is that you will get a scattering of this form, like dark matter and neutrino interactions. So now you can compute one and compute the cross section, and you will see that the cross section can be and have two types of temperature dependence. If the masses of the dark matter mediator are actually degenerate, you can have a constant interaction, or if they're non-degenerate, which is a normal case, you can have a temperature-dependent interaction, temperature-square-dependent interaction. And so what is important is the scattering rate, and you parameterize the scattering rate by these two numbers, U0 and U2 for these two cases, where you just normalize the cross-section by sigma Thomson and mass to 100 GeV. So before that. So this interaction will affect both the scalar and the tensor modes of the CMB, because you're coupling all these two ingredients, dark matter and neutrino, with each other. So first, let us look into what is happening with the B mode. I will come to the E mode, scalar mode constraint later. So this is the evolution equation of the gravitational waves, normal gravitational waves. So you have at the left-hand side, you have the Hubble constant over here, and on the right-hand side, you have an anisotropic stress of the medium. And the dominant contribution of the anisotropic stress comes from the free-streaming particles, which are neutrinos. And you can actually show that this term, if you consider the full set of equation, the right-hand side actually is a sinc term. So essentially what you are doing is that when you're introducing the new interactions, you are suppressing the growth of this anisotropic stress. So what you are doing, you're suppressing your sinc term compared to lambda CDM. So hence what will happen is your gravitational wave amplitude will be enhanced compared to lambda CDM. So this is the effect we are looking. So there is an enhancement of the gravitational wave compared to lambda CDM, and we want to pinpoint this effect. So let's first quantify the effects. So this is the standard. This is a standard effect due to standard model neutrino interaction. So where the neutrinos decouple and free stream after that. So depending upon what is the strength of your new interaction with dark matter and neutrino, you can have an epoch which we call a dark matter neutrino decoupling, where the mean free with essentially the same definition, where the mean free path of the neutrino due to dark matter neutrino interaction is equal to the Hubble scale. So remember. So let's understand this plot. So what is plotted here is a co-moving horizon, and with the co-moving mean free path of the neutrinos for these two different parameter choices. Now, if we do not have any new neutrino interactions, neutrino mean free path is already super horizon in lambda CDM in this redshift range. Now, because I introduced this new additional interaction, we see that below this redshift, where the small scale modes enter the horizon, we have the neutrino mean free path is below the horizon, so we have an effective suppression of the anisotropic stress, so we will have an enhancement of the gravitational waves in this range for the small scale modes which enter in this range. And the mode that enter in this range, actually because the neutrino is already super horizon, we do not expect any effects. So this is exactly what we expect, that the small scale modes will be enhanced compared to lambda CDM, whereas the large scale mode will have more or less a similar type of behavior with lambda, like lambda CDM. Okay. So this is just, I don't think we need this slide over here, but I just wanted to make the point that the effects that we will be showing here are actually on the unlensed B mode. So because, gravitational lensing of the structures can also affect some, get B mode polarization from E mode. So you have to first, to see this effect, go to this unlensed B mode, and all our plots are for unlensed B mode. So let's see what's the effect on CMB B modes. So this is the plot. So see, what I have plotted here is the fractional change of B mode spectrum compared to lambda CDM with multiple. So 0 is the lambda CDM line. And see, for a given interaction strength, what is happening is the small scale modes, because small scale modes which corresponds to modes of higher and higher L are getting enhanced. So effectively what I'm seeing is an enhancement of the B modes at a large multiple. And essentially, if I jack up the interaction strength, I see the more enhancement. And so while plotting all this interaction strength, I have fixed the value of NT, which is a tensor spectral index, to its lambda CDM, consistency condition from single field solar lambda CDM, that your, so just NT is minus R by 8 or something. Yeah, and so if you take the constant, it is nearly 0 in lambda CDM. So now look at this plot. So this plot, for this plot, what I have done, I have shut down neutrino interaction, but I have changed the value of NT to a positive number. So therefore, I see that both these effects, so this is a primordial effect. So for this change is coming from the initial power spectrum, whereas this change is usually coming from the medium effects. So, and we see that both these effects actually push the power spectrum, enhance the power spectrum in a similar direction. So this is the degeneracy I've been talking about. So, but as you can always see that the shape of these two modifications are very different. So in principle, if you have a high precision measurement of the CMB mode, you can disentangle these two effects, and you can turn this argument around, that then you can prove the new physics interactions of neutrinos through CMB modes. But if, let's say, you do not have very precise first B mode measurements, then, and also if these effects are small, so these two can be actually fairly degenerate. So therefore, this is exactly the title of my talk, that you can, so additional neutrino interactions can fake blue primordial spectrum of, for this case. And so this is for temperature dependent interactions, temperature independent interactions, and this is the similar thing that you find for actually temperature dependent interactions. So now the key takeaway here is that there is much more rich information is hidden in the CMB mode just beyond the tensor to scalar ratio R. So now so the first question that should arise in your mind is, what is the bound on these parameters that you're talking about, the neutrino interaction strength? Because essentially that also modifies the scalar mode. So essentially there are bounds on this interaction strength from the CMB scalar modes. Like if you include the Planck and also some large scale structure data, you can draw some pretty competitive bound on the CMB on this interaction strength. So essentially, if you just take this constraint on their face value, then you see it. So this is like 10 to the power minus 4, right? So this is somewhere over here. So the naive expectation would be that, okay, this effect exists, but this effect is very small compared to, staying within the bounds of these things. But this is actually not always true. So here comes multi-component dark matter. So what I have done in this is kind of a proof of principle that these bounds can be relaxed from the scalar mode. So there is, let's say there is dark matter consists of two type of dark matter consists of two components. One interacts with the neutrino, one do not interact with the neutrino, which is a normal CDM. So essentially what is happening is that your scalar mode is actually affected by both dark matter and neutrino, because dark matter and neutrino are coupled. So essentially you should see some acoustic oscillations in the dark matter, so that will have some bounds from scalar mode, and also because neutrinos are not free streaming, that will definitely have some bounds. But if you look at the tensor mode, the dark matter is doing nothing for tensors. So tensor is all about neutrinos. So essentially the dark matter the effect on the dark matter do not affect the tensor mode. So if you can go to a parameter space where you can get rid of this constraint, you will not change your tensor mode constant, but essentially you will relax the CMB scalar mode constant. So this is exactly what will happen if you take this limit that you say, just take this limit that f goes to 0, keeping f times u equal to constant. So what you will see that then see your delta dm is basically delta CDM. So there is, it's behave CDM-like. So this constraint is gone, and what you are left with the some effects from the neutrinos. So this is exactly what we see in this plot. So we have done a MCMC analysis of the CMB data with the inclusive 2 constraint, which is a fraction of interacting dark matter and the interaction strength. And we see this fact that when I go down in the fraction of interacting dark matter, I can improve the exclusion, the upper bound on these parameters f time u by fairly order of magnitude number. So this is also something you will, so this was for, I think, temperature dependent interaction. This is the same thing that we are happening for temperature independent interaction. So see what is happening here, that when you have a, let's say, 100% interacting dark matter, all the dark matter of your universe interacting with the neutrinos, the bound is pretty strong. So it's like 10 to the power minus 4. But as I go to a fraction of interacting dark matter, as I see the bounds change, drastically, it gets relaxed, and also the bounds on f times u actually improves by 2 order of magnitude. So essentially, what you are looking for a percent level effect here, suddenly in this model, staying within the constraint of CMB scalar modes became some effect like some 20% effect. So these effects on CMB B mode can be very real, because so it is not always true that these effects are small. There are models where this effect can be enhanced, and we do not know the answer yet. So I think I would stop here. So these are my conclusions. I just want to read it out for you. So the key point is that dark matter neutrino interaction can stop neutrinos from free streaming. So therefore, for that case, CMB B mode will be enhanced, and the new interactions sometimes mimics the blue tensor spectrum. And also disentangling these effects need actually very small scale measurement of CMB B mode and efficient delensing. And also if the neutrino interact with a small amount of dark matter, so this effect can be enhanced by order of magnitude. Therefore, we have to be careful. So if we actually see a departure from scale invariance in same beam mode experiments, then we should first be careful to see whether it is coming from the primordial effects or there is something happening with the neutrinos. That's all of it. Thank you.
All right, we have a question up top first. Is there a microphone up there?
Yeah, hi. I'm just a little unsure. I'm just trying to understand your maybe perhaps terminology. So I'm confused by your statement that gravitational waves are enhanced because surely, free streaming neutrinos suppress gravitational waves. Yes. Weinberg calculated this some time ago, and you're just saying the suppression is less. Right? If you take into account interaction. So it never really takes a red spectrum in terms of blue. It's still red. So if something is naturally slightly red tilted, right? That's what we expect from inflation.
Yes.
And then neutrinos cause an additional suppression because of anisotropic stresses in free streaming.
Yeah.
And you're erasing that effect.
I'm erasing
that. So you're erasing the suppression, but you can't take something that was red and turn it blue. You're just making it go back to what it was originally, which is still red.
No, that actually depends, right? These two effects compete. So there is you're saying that there is a tilt coming from neutrino.
So with zero source on the right-hand side, gravitational waves are red, right? So adding interactions will not take zero and make it positive, right? It just takes something that suppresses it and keeps it back to zero again.
Okay, let me say it in a different way. So when you have a dark matter power spectrum, full dark matter, gravitational wave things, that you have a primordial part and you have a transfer function, right?
Yes.
My point is that you are saying that if primordial spectrum is redder, but there are something happening with the transfer functions that is actually enhancing the signal a little bit. So there is two effects, right? So one is because if you're saying they're slightly red, because if you consider normal inflation, so these are slightly red, but there is an enhancement coming from the transfer functions. The whole effect can
No, but the transfer function is never enhanced, they suppress, right? You're just reducing the transfer function, right?
No, I'm enhancing it, right? So, okay, just let me go back.
No, okay, look, so you agree that in a universe without neutrinos, That's what I'm trying to understand. But there's no, you don't turn a red spectrum blue. Okay, good. Now, okay, thank you. That's what I want to understand. And my next comment is there's also effects from, so Komatsu and Watanabe actually calculated some years ago the effects from, changes in temperature redshift relation from just a standard model. So there's a feature, for example, from the QGP transition as well. So how does those two effects compare? Because that can actually give you quite large localized changes in the transfer function that,
So the point for the QGPs is that that actually happens at very larger, so the modes that enter at that time, so this is, the temperature of the so you see the effects are at the redshift, in modes are entering at the redshift of 10 to the power 4 or something. So these are fairly, temperature is less than EV or something, but I think if you're talking about the QGP phase transition, that's some 100 MeV kind of, phase transition that is happening at some 100 MeV, so that will affect at a different scale than this. Models.
Okay, naively, are you also changing this neutrino temperature at some later time? So this has no effect on the neutrino temperature.
So the entropy transfer between dark matter and neutrino is small.
All right, in the interest of time, let's thank the speaker and move on to the next talk, please.